Hey everyone, welcome back to The Explainer. Today, we're diving into a genuinely fascinating math puzzle. And look, I promise to completely demystify calculus for you today. No dusty academic jargon, I swear. We're just going to look at how things change in the real world and how we can measure that exact moment of change using some truly elegant tools. Let's get right into it.
So, imagine you're pouring water into a cone-shaped glass at a perfectly steady, constant rate. You'd probably expect the water level to rise steadily too, right? Well, it doesn't. It actually rises slower and slower the fuller the glass gets. Have you ever wondered why that happens? Or better yet, how we can calculate exactly how fast that water is rising at any given split second? To solve this little riddle, we first need to build a couple of really basic mathematical tools.
All right, the basics of changing things. At its absolute core, calculus is incredibly simple. Seriously, it's really just the study of how one thing reacts when another thing changes. It is just cause and effect, quantified. Now, you've probably seen this classic equation before. Y equals f of x. But let's translate that into plain English, okay? The x is simply the thing we control, the independent variable. And the y? Well, that's the thing that responds. If you change x, y reacts. Think about it like a circle. If you change the radius, the area responds. It's just cause and effect. And this perfectly highlights the difference between two types of change, average rate and instantaneous rate. Think of the average rate kind of like a road trip. Say you drive 100 kilometers in 2 hours. Your average speed is 50 kilometers per hour. But you weren't driving exactly 50 the whole time, right? You sped up to pass, you slowed down for traffic. Your instantaneous rate, on the other hand, is exactly what your speedometer says at one specific frozen second in time. Calculus is basically the mathematical version of that exact instantaneous speedometer reading, finding the exact rate. So how do we actually calculate that instantaneous, right now, speedometer reading using math? Well, if we want to know how fast the water is rising right this very second, taking an average over the last minute just isn't going to cut it. We have to shrink the gap. To find that exact rate, we use a pretty clever little trick. In math, we use the Greek letter delta to mean change in. So delta x is a change in x, and delta y is the response. To pinpoint the exact rate, we just make our change in x smaller and smaller. We take it from 1 down to 0.1 to 0.01 down to 0.001. We're closing the gap. We're squishing that interval down until it is practically 0. And when we do this, the resulting division of delta y over delta x approaches a very specific number. In calculus, we call that approach the limit. And that limit brings us to our golden rule, the derivative, usually written as dy over dx. Now, I know this symbol looks a little scary to some, but I promise you, it simply means the exact instantaneous rate of change. It literally just asks, how fast is y changing when x changes, at one precise moment? Let's look at a quick, practical example just to solidify this. If dy over dx equals 4, it means we have a multiplier effect. For every tiny, microscopic change you make in x, y is going to change 4 times as much. Simple as that. Okay, now that we have our mathematical tools, let's put them to work. That brings us to the water cone problem. To make our calculus a bit more grounded and, honestly, maybe a bit more whimsical, let's imagine a water fairy who is stuck with the very specific chore of filling a magical cone-shaped tank. This fairy needs our help to figure out exactly what is happening to the water inside. So, here are the specifics of the fairy's tank. The cone has a top radius of 8 inches and a total height of 9 inches. The fairy is pouring water in at a perfectly constant rate of 100 cubic inches every single second. Our goal, the ultimate riddle of this whole explainer, is to find out exactly how fast the water depth is increasing at the precise moment the water is exactly 6 inches deep. Let's translate this physical tank into our math puzzle by setting up some variables. V is going to be the volume of the water, and H will be the water depth. Now, we already know the rate the volume is changing over time. That's dV over dt, which is 100. What we're desperately looking for is the rate the height is changing over time, dH over dt, specifically at the exact moment when H equals 6. Now, here is a really cool trick. A cone full of water actually creates a smaller water cone inside the tank. And because they share the exact same shape, their dimensions are perfectly proportional. If the whole tank has a radius of 8 and a height of 9, well then the ratio of the radius to the height is always going to be 8 to 9. Therefore, the radius of the water surface, r, is always equal to 8/9 of the height h.
This proportional geometry is the magical bridge between the physical shape of the tank and our calculus equations.
Connecting the rates, now that we have our geometric bridge, let's connect it to our derivatives and finally crack this puzzle wide open.
We're going to start with the standard formula for the volume of a cone. V equals 1/3 pi r squared h. But having an r and an h in there is just messy. We only care about the height. So we take that magical bridge we just found, r equals 8/9 h, and we substitute it right in for r. After squaring it and multiplying it all out, we get a beautiful new formula. V equals 64 pi over 243 times h cubed. Notice what we've done here. We now have a formula that describes the volume purely in terms of the water's height. And now it's time to differentiate. We take the derivative of our new volume formula with respect to the height. We multiply by that exponent of 3, which simplifies the fraction. And we are left with this. dv over dh equals 64 pi over 81 times h squared. This specific equation is an incredibly powerful tool. It tells us exactly how quickly the volume changes in response to a change in the depth at literally any given height. So let's go ahead and plug in our target depth. Remember, we want to know what's happening when the water is exactly 6 inches deep. So we plug 6 in for h. 6 squared is 36. After doing a little bit of multiplication and division, we get 9 times 256 times pi, which comes out to approximately 89.36. This means that exactly 6 inches deep, the volume is increasing by about 89.36 cubic inches for every single 1-inch increase in depth.
But wait, we aren't quite done yet. We need to connect this whole thing to time, because the ferry is pouring water in every second. This introduces the chain rule. Think of it as a logical chain of events. Time changes, which causes the water depth to change, which causes the water volume to change. Mathematically, the rate of volume over time is equal to the rate of volume over height multiplied by the rate of height over time.
We know the water enters at 100 cubic inches a second, and we just figured out that at 6 inches deep, the volume changes by 89.36 for every inch of height. So we simply divide 100 by 89.36, and there is our answer, 1.12 inches per second. The ferry can finally rest easy knowing that at the exact split second the water hits 6 inches deep, the water level is rising at a rate of 1.12 inches per second. The real lesson. So what's the big picture here? What is the core takeaway that this related rates problem is actually teaching us about the physical world and mathematics? What's truly fascinating is comparing these two realities side by side. On one hand, we have 100 cubic inches per second. That's the raw volume entering the tank. On the other hand, we have 1.12 inches per second. That is the rate the height is actually increasing. Guys, these are two completely different physical realities. One measures a 3D amount of space filling up, the other measures a 1D line moving upwards. They are intricately connected, absolutely, but they are definitely not the same thing. And this brings us right back to our opening puzzle. Why does the water level rise slower and slower? It's entirely because of the physical shape of the cone. Down at the narrow bottom, 100 cubic inches of water forces the level to shoot up quickly because, well, there just isn't much room to spread out. But as the cone gets wider at the top, that exact same 100 cubic inches has to spread out over a much larger surface area. Therefore, the depth rises much more slowly. The rate of the height change depends entirely on how high up in the cone you are. It's just brilliant how the math perfectly proves our intuition. The real engine that allowed us to figure this all out is the chain rule. It's simply a mathematical way to connect the rates of two different quantities that both depend on time. If you understand this formula, you intuitively understand how cascading changes work in mathematics. You can seamlessly link cause to intermediate effect all the way to the final outcome. So, if you ever need a straightforward framework for cracking any related rates problem, just follow these 4 steps. First, understand the geometry of the physical space. Second, write a formula connecting the things you care about. Third, take the derivative to find the instantaneous rates. And fourth, use the chain rule to connect those rates to time. Geometry, equation, derivative, time rate. It really is that simple. We have successfully measured a cone today and found the exact speed of rising water. But take a look around you. Literally, everything is in motion. The swelling of traffic on a highway, the cooling of a cup of coffee, the expanding shadow of a building as the sun sets. These are all related rates. Now that you have the tools to see them, what other invisible rates of change are shaping the world around you right now? Keep observing and keep learning.